This is Chemistry 351. My name's Josh Price, and you are the few and the proud who are here in spring term to take one of the hardest classes that you can take at BYU. I feel like many of you might be sort of sitting here with your lightsaber telling Master Yoda that I'm not afraid. And then creepy Yoda sort of looks back at you and says, I don't know, he has teeth kind of like that. You will be. You will be. All right? So I won't tell you anything about the syllabus today in terms of how the course is going to run. You can go download that on Learning Suite and read it. Your key to success in the class is going to be giving yourself time ahead of class to do the reading, to work problems, and to identify your misconceptions. There's a section in the syllabus where I talk about what happens when you think you've studied hard but you get a bad grade on an exam. I have that conversation with people every semester. The syllabus will tell you how to avoid that, so please take a look at that. There are study guides and practice exams that are designed to help you along the way. In a lot of ways, you're really, I feel like I wish I was you, because I can remember taking this class 20 years ago. No, it's not been 20 years. It's been almost 20 years ago. No, it's been more than 20 years, sorry. In the fall of 2001, fresh off my mission, I had Chemistry 351 from Professor Savage, who's still here and who's a colleague and a good friend. And it really opened up the world to me. My goal for you in this class is to, and in 352 really, is to give you the tools you need to understand the world around you at the molecular level. Coupled with that, I want you to have an appreciation for the beauty of creation and the power of the great creator. One of the coolest things about my job is the ability to learn new things. So all the time I'm up in my office in my research trying to develop skills I didn't have before, and it's just like, it's awesome to me when a light bulb clicks and I have an aha moment. So hopefully we'll have a lot of those together. Now we're going to start our discussion today. Oh, and I'll just mention, I don't broadcast lectures by Zoom, but I do record lecture audio and video, and I'll post that on Learning Suite shortly after class. So if for whatever reason you get behind or want to review things again, notes and video will be posted. Okay, so we're going to start today by talking about waves. And we're going to think about waves as just sort of being a sine wave or a cosine wave. I can't remember which, but we'll use sine. And close enough. And maybe from physics or math, you're used to the idea that waves can be superimposed on each other and add together. So if, for example, I have, we'll make this wave blue or something, and suppose I take another wave of the same frequency, same amplitude, and I add it to the first wave sort of at the same point, in phase, we might say. We add both of these two waves together. What's going to happen is we're going to get constructive interference. Does that sound familiar? Heard about that before? So sorry about the handwriting, I'll try, but I'm also sorry about spelling errors. It's harder than you could think than you might think to talk and write / draw at the same time. So sometimes it doesn't go particularly well. So yeah, we would add these two waves together, and we're going to get a wave that has the same frequency but higher amplitude, right? However, if we were to subtract these one of these waves from the other, and let's just assume for the moment that they again have the same amplitude, and we're subtracting them with the same frequency. See, there's a spelling error. I can't, sorry. Subtract. What you're going to have is called destructive interference. And the sum of those two waves would just be 0, right? So we're used to the idea of waves being able to cancel each other out. If you've ever been in a poorly designed auditorium with speakers, sometimes there are dead spots in the room where you can't hear very well because the sound waves from the speakers cancel each other out at those points. Points where the wave magnitude or amplitude is 0 are called nodes. So in this wave, we have every time the wave goes through 0, we could call that a node. Interestingly, the wave exists even when its magnitude goes to 0, right? It's just a mathematical quantity. We haven't even said what the x-axis is. This could be space or time. The y-axis is amplitude. But the magnitude of the wave can be 0. And it turns out that the higher frequency of a wave, the more times it goes through 0. So the wave I just drew is, whoops, now it's going to make it look like, sorry. So the higher frequency of a wave, the more times it goes through 0. If you compare the wave that we've drawn above with the other wave we've drawn below, the one in black has a higher frequency, shorter wavelength, and therefore goes through 0 more times. Why are we talking about waves? Well, because in this class we're going to think of electrons as basically standing waves. You've seen a standing wave before. If you haven't, go look it up on Wikipedia or go buy a Slinky and play around with it. A standing wave is a wave that's constrained, that has certain constraints on it. So imagine a violin string or a piano string or a pipe organ. You constrain the string at 2 different points, and then based on the length of the string and the properties of the string, there are certain waveforms that are allowed. One of them is like this, right? Another is like this. Another would be, is that looking at all familiar? You've seen standing waves before. We're going to think of electrons as standing waves. That is, they're wave-like particles that are under some constraint. And that is, what is the constraint? Well, the attraction between an electron and a negatively charged electron and a positively charged nucleus. And we're going to call the standing waveforms that an electron can adopt, we're going to call those wave functions or orbitals. So you probably heard a little bit about wave functions and orbitals in 105 and 106. If a lot of that's unfamiliar to you, there's some background in a molecular orbital theory study guide that's posted on the content page of Learning Suite. That study guide will take you through the math of quantum mechanics and MO theory in greater detail than I really expect you to get, but it'll provide at least some background. Fortunately for us, the qualitative picture is going to be good enough. So let's talk about the electron wave functions that are present in the simplest of hydrogen molecules, or the simplest of all molecules, and that is molecular hydrogen. So you've been taught about covalent bonding, and you've viewed it in terms of one of these two Lewis structures where a line represents two electrons shared between two atoms, or maybe you drew it this way. And I think in terms of bonding, you learned that covalent bonds happen so that electrons can fill their valence shell, which is a decent enough explanation, but it's really more of a mnemonic device, and we want to dig a little bit deeper and determine why bonding happens. So let's talk about the wave functions that are available to the hydrogen atom. And these are the orbitals that you've learned about. And the one that's available to hydrogen is simply the 1s orbital. And you've learned about that. It's a spherically symmetric orbital. It's just if the hydrogen atom is in the middle, the 1s orbital is simply a sphere about that atom. When we draw orbitals, we're really drawing an area within which a certain percentage of, we have a certain percentage probability of finding the electron. To illustrate this point, I'm going to plot the wave function of the 1s orbital, or the 1s wave function, on this pair of axes. The y-axis is going to be, again, amplitude, and the x-axis is going to be r, or distance from the nucleus. And so if you were to plot sort of the wave function for the 1s orbital of hydrogen, what you would see is something like this. It peaks at r equals 0 and then trails off in either direction. And it approaches 0 amplitude as r approaches infinity, but it never quite gets there. So there's always a finite probability of finding the electron really, 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 really far from the nucleus. And in fact, the only way to know that there's a 100% probability of finding the electron is to let r go to infinity, which is another way of saying, yes, the electron is in the universe, which is not a particularly useful statement. And so what we do instead is we say, okay, I want to know the area within which 95%, I've got 95% probability of finding the electron. So maybe that's, you normalize the area under the curve and you say, okay, the whole area under the curve is 1. I want to know the radius at which I've got a 95% chance of having the electron in that area. And then we draw that, okay? That's what the 1s orbital looks like. So I will mention that the 1s orbital is a wave function. In quantum mechanics, the symbol for the wave function is the Greek letter psi. I remember that it's called psi because it looks like the weapon from Teenage Mutant Ninja Turtles that Raphael used. Now, that's probably before your time, I realize that, but if you can go Google it and figure out the reference. I am a huge Star Wars nerd, though, so there will be Star Wars references throughout the class. Just indulge me. If you hate it, just sort of roll your eyes. You can laugh at me as well as with me. I can't really tell the difference, so that'll be fine. These wave functions are solutions to the Schrödinger equation. And you've seen that equation before in, I'm sure, 105 or 106. The little hat indicates that h is a mathematical function. And the h is called the Hamiltonian operator. And it's a mathematical function that, if you apply it to the wave function, returns the wave function itself times a constant. And that constant is the energy of the wave function. Now that looks simple, but it turns out that the Hamiltonian operator it can be kind of complicated because it contains both kinetic energy and potential energy terms for our purposes for the electron. So far, so good. A particle that has mass should have both potential energy and kinetic energy. The potential energy part just comes from Coulomb's law, and this is pretty simple. Basically, closer to the nucleus is lower in energy or more stable. Does that sort of make sense-ish? And we could write Coulomb's law. It's like some constant, charge 1, charge 2 divided by R, and I think that gives you the energy. I could be wrong, but basically the closer you are to the nucleus, the smaller R is, the bigger the potential energy is. Kinetic energy of the electron, well, that would be from physics just sort of 1/2 times the mass of the electron times the velocity of the electron. And to know the velocity of the electron, you need to know what the wave function is. Now, I'm not going to go through the math to derive this, but basically, the following function, when applied to the wave function, returns the kinetic energy value. So it's h bar. Bar is just Planck's constant divided by 2 pi. M is the mass of the electron. And then, and you're going to love this, the second derivative of the wave function with respect to space. In this case, we're just dealing with one dimension, so that's good enough. But in 3 dimensions, we will sometimes represent this with an upside down triangle. That's a del operator. It just means second derivative. So something about the second derivative of the wave function tells you how much kinetic energy it has. Well, that's useful. Thank you for that. What is a second derivative of a function with respect to the x-axis? What does that mean? First derivative is what? Slope, right? So right. So here is a function. Maybe this is x squared. So first derivative would be slope at any given point. What about second derivative? Change in slope, rate of change in slope. Wait, I wrote 2 changes. See, told you couldn't do it. Right, first derivative is slope, second derivative is rate of change of slope. So remember how I told you before intuitively that wave functions or waves that have higher frequency have greater energy? We can apply the second derivative reasoning to that. Oops, didn't mean to delete that. In which of these functions, red or black, is the slope changing most? Black. And you can tell because it goes through 0 more often. In order to do that, the slope has to change quicker. I'm not sure how to explain that. Can you see how the slope is changing slower in red than it is with black? Okay. So we would say that the black function has a higher second derivative with respect to distance, and therefore has higher energy if this were an electron wave. Faster changing slope. That's going to be a general observation in organic chemistry. Wave functions that change slope slowly are lower in energy. And one of the ways you can see from our example above, one of the ways that you can spread out or make a wave function change slower in slope is simply to spread it out more. Do you see how the red wave is sort of has a longer wavelength than the black wave? So what we will get from this definition of kinetic energy is that spreading out of electrons in space is stabilizing and allows them to move lower in energy. Okay, so with that in mind, we're prepared to take the wave function for one hydrogen atom and think about how to take two hydrogen atoms and put them together and make a bond. But before we do that, any questions you want to ask? Yes?
What was that symbol with the H line through it over the two ends?
Oh, sure. So M here is the mass of the electron. H bar is Planck's constant divided by 2 pi. And Planck's constant we get from the definition that the energy of a photon is Planck's constant times its frequency. And there are some other uses. Okay, other questions? Yes?
So in Coulomb's law, is it saying that like the closer the electron is to the nucleus, the lower potential energy it has?
Yep, the closer the electron is to the nucleus, the lower potential energy it has. It's exactly, I mean, it's, for our purposes, it's the same in our macroscopic world with gravitational potential energy. Here on the first floor of the Benson building, we are closer to the Earth and therefore we have lower potential energy than on the fourth floor of the building. So yes, we change energy states as we move from the top floor to the lower floor. Same thing, and in general, we're going to see that as a general principle in OCHEM. Closer to the nucleus is more stable. That's going to be one of our explanations as to why a pi bond is not as stable or low in energy as is a sigma bond, but we'll come back to that. Other questions? Yeah? Yeah, so it's an interesting question. The question is, it seems maybe like you've got two offsetting things, that the closer you get to the nucleus, the lower you are in potential energy. But then if you're going to constrain something to be closer to the nucleus, the slope is going to change more and you'll have higher kinetic energy. Yes, and in fact, it's the balance between those two that gives the orbitals their particular shape. Yep. Okay, what else? All right, now I'm not going to be asking you to take second derivatives on the exam or to do math, really much math. I think if you can count, if you can subtract small numbers, add small numbers, and divide by 2, you should be okay. All right? So hopefully that's reassuring. All right, let's consider our simplest organic molecule, hydrogen. And as I told you, each of these hydrogen atoms, we'll call one A and the other B, as though we could tell the difference between the two. And each of them is going to come with a 1s orbital that looks like this. Okay, so let's just say this is HA, and then I will take sort of on the same axis, we're going to put HB. And we'll make this one blue. I'm sorry about the copying pasting, by the way. I realize that for those of you who are using pen and paper, that's irritating, and all I can say is, sucks to be you. No, no. I mean, sorry. I will, but I like using the iPad because it makes sure everybody can see. It also gives me the chance to use color and zoom in or zoom out. If you prefer the chalkboard, that's great, but I don't, so I won't use it. In any case, the notes will always be posted, so if there's something you can't scribble down, that's fine. So let's now imagine taking the 1s orbital from hydrogen A and adding it to the 1s orbital from hydrogen B. We're going to allow them to overlap. Now, at some point, as we do this, we're going to reach a point where the we're going to reach a point where the nuclei start repelling each other, right? Because you got two positively charged nuclei. And so at some point that's going to totally overwhelm any stabilization we get, and there's going to be some equilibrium distance between the two hydrogen atoms. Okay, this is going to be the constructive interference combination where we simply add together the wave function for the 1s orbital of hydrogen A and the 1s orbital of hydrogen B. And if we were to draw the sum of these two, or what we would expect, it would look something like this. As we got closer, we would be a little bit higher here. And then in the middle, we wouldn't drop down quite as much, and then we would go there, right? That's maybe not perfect, but that's the idea, is that we add the amplitudes together and we get a new wave function. Okay? There's a little bit of nuance here that I'm deliberately oversimplifying. If the area under the curve for any orbital has to be 1 because the probability of finding the electron in the universe has to be 1. If you add two curves together and the area under each is 1, the sum of those should have an area of 2, which we can't have. So if you ever see somebody plot this, actually the magnitude here will be a little bit lower. I'm sorry if that was confusing. You're welcome to just ignore completely. But this is what we would get if we added those two wave functions together. Simply the constructive interference. All right? Questions about how we got that? And please remind me when I don't move the cursor so that little annoying record box is gone. All right. Questions? All right, so what? Who cares? You do because you're afraid it will be on the test, but there's a bigger reason to care than that. Let's look at what we expect the energy of this wave function to be based on what we said before. The Hamiltonian operator contains a term for kinetic energy and a term for potential energy. Okay, so I guess it should be negative, right? Because closer to the nucleus you get, the lower the r distance is, the more negative the number is. So this is kinetic energy, and this is potential energy. Now, think about the electrons in this section between the two nuclei. Are they closer or farther away from the nucleus than they would have been in an isolated 1s orbital? What do you think? They're closer. They get to experience two nuclei instead of one. So that should be some favorable potential energy. Now let's think about so our 1sa plus 1sb orbital is close to two nuclei, so that should be a favorable stabilizing thing in terms of energy. Now let's think about kinetic energy. Think about how the slope changes for the individual s orbitals versus this combination. Does the slope change faster or slower, particularly in this region? Changes a lot slower. So, okay. So we concluded that it's lower in kinetic energy between the two nuclei, and that should be a stabilizing effect. So this new orbital that we're able to make from each of the 1s orbitals is actually lower in energy than either of the 1s orbitals themselves. In other words, combining those two 1s orbitals from hydrogen together gets us to a lower energy state for our electrons. And this is a covalent bond. This is what a covalent bond means. We can illustrate that with what we'll call an orbital energy diagram. To do this, what we'll do is we'll have, running out of space. That's okay, we'll just zoom in. On this axis, we're going to have energy. And about this point is going to be where the energy level for our 1s orbital for hydrogen A is. And then over here, we'll put our 1s orbital for hydrogen B. This is sort of our, we may put a dotted line here to just indicate this is our break-even point in terms of energy. In other words, if where energy is at this level, we're at the same energy as just a hydrogen atom with a single electron, no bond formed. But what we just said above is that when you add those two orbitals together, the combination of the 1s orbital on A with the 1s orbital on B is this new orbital that is lower in energy than either of the starting orbitals. There's a difference in energy here. And because of that, the electrons that we start with, one here and one here, are going to end up in this lower energy orbital. And it will be favorable for them to be in that lower energy orbital because they're lower in energy. Okay, and this is what we call a bonding orbital. It's no longer an atomic orbital because it's an orbital that spans the whole molecule, so we're going to call this a bonding molecular orbital. Now, if we were to look at what this bonding molecular orbital is, what it appears like, if we labeled the positions of HA and HB, this bonding molecular orbital is going to basically look like this, sort of an oval that surrounds hydrogen A and hydrogen B, and I'm just coloring in that space to give it some definition and to match the color that we saw above. Electrons in this orbital are going to be closer to the two nuclei, and their slope is going to change more slowly, so overall we're lower in energy. Okay? Yes?
When we're talking about that graph of the waveform and the yellow line, when we're talking about the electrons there, is that like the possibility of being within that distance? Is that both electrons?
Yes, this is good question. Yeah, so does the orange line here where we added those two wave functions together, does that represent a single electron or both? The answer is yes and no. So technically, each wave function is defined by the quantum numbers that you learned in 105 and 106. There's a principal quantum number, and then there's another one, and then there's another one, and another one. One of them, let's see, it's like, oh shoot, now I feel stupid. One of them's angular momentum. Anyway, N, L, M, and then There's another M for spin, right? And electrons can have an upspin or downspin. Technically, the upspin and the downspin are two different wave functions, but other than spin, they have the exact same spatial distribution. So it's just easier to say, oh, one wave function, one orbital can accept two electrons as long as they have opposite spin. But so that's what I'm saying. What I've drawn here is the wave function for each single electron, one with upspin, one with downspin.
Okay, so it's not them together, but it does represent both electrons.
Yeah, it's not necessarily them together, but it does represent both electrons. And for our purposes, that's why I drew it this way. We're just going to think about this as one orbital or one wave function that two electrons can have. Okay? What else? Another hand? No? Okay, so this is why a covalent bond happens, because it allows electrons to move lower in energy because of lower kinetic energy and lower potential energy. Now, one thing that you may not have learned about before is that the math of mixing atomic orbitals together requires you to deal with not only the plus, but with the minus combination. You can think of it as sort of a conservation of orbitals principle. Two atomic orbitals in, you got to get two molecular orbitals out. And we've only got one here. This is our bonding molecular orbital. Let's try to deal with what the minus combination would look like. So, I'm going to be nice and redraw things, even though I could have copied and pasted. How magnanimous of you. All right, there's our position of HA, there's our position of HB. Here is the wave function for A. And it tails off like that. Now let's say we subtract the wave function for A from the wave function, or subtract the wave function from B from the wave function for A. This would be like we do something like this, right? Okay. So this starts to get a little complicated. Let's draw in orange what we expect this to look like. Okay, and remember we're adding or we're subtracting the wave function for B from the wave function for A. So this is now destructive interference, like we talked about before, right? We're just doing math, pluses and minuses. So what we'll see in orange for the sum is out here. It'll basically match the red part, but as we start to get closer and closer, some of the negative blue wave function is going to cancel out some of the positive red wave function, so our peak is going to be lower. And then about here, in the middle between the two nuclei, the sum's going to go to 0. You see that? You have a positive number and a negative number that are more or less the same magnitude. But actually, if you look, your blue curve is not exactly opposite the red curve. Okay, fine. Who am I talking to? Okay. That's going to be a place where our wave function goes through 0. So we're going to slope down more precipitously and go through 0. And then on the other side, we'll have something like this. Okay? And so what you see for the minus combination is a wave function that instead of being positive everywhere, is positive on one side and negative on the other. All right? And just to highlight that point, we can let's maybe use orange color for all of the parts of the curve that are that are above 0. And then let's use maybe purple for all of the parts of the curve that are under 0 or less than 0. Okay. Questions about how we got that? Ish? No? Okay. So what does this mean? Let's talk about potential energy and kinetic energy. If an electron were to adopt this wave function, is it going to spend time closer to the nucleus or nuclei or further apart? Further apart. Actually, the majority of the area under the curve is in the space outside the two nuclei. In contrast, in the previous orbital, most of it was between the two nuclei. Okay? So higher potential energy because electrons here would be farther from the nucleus. And yes, I don't actually know really well when to use further versus farther, and please don't tell me because I don't care. There are commercials on the radio about that. Maybe you've heard them. Anyway, kinetic energy. Is the slope changing faster or slower than the original 1s orbitals? Changing faster, you can tell that because it goes through 0. And you can tell that the slope is getting more negative here than it did in the isolated orbitals. So slope changes faster, higher kinetic energy. So this orbital combination of the 1sa minus 1sb is actually higher in energy than the starting 1s orbitals are. It's there and it exists, but it's higher up in energy. So this will be the 1s orbital A and the 1s orbital B, minus 1sb, and this is going to be higher in energy than our starting orbitals. Because of that, we're going to call it an anti-bonding molecular orbital. A couple of things. In general, we find that the stabilization or this change in energy for the bonding orbital is less than the destabilization for the antibonding orbital. In other words, mathematically, we would say the difference in energy between the antibonding orbitals and our starting orbitals is bigger than the difference, the absolute value of the difference between our bonding orbital and the starting orbital. So if we were to take 2 additional electrons and dump them in this system and try to make H2 2-, the only place those 2 electrons could go would be here in the antibonding orbital. Now draw some conclusions, make a prediction. What's that going to do to our molecule?
Make it less stable?
Make it way less stable. If I put electrons up here, that's going to completely cancel out and then some the stabilization I get from having the bonding orbital. Do you see if this distance here is bigger than this distance there, and if we put 2 electrons up there, suddenly our system isn't stable anymore. Suddenly we get 0 stabilization from having those 2 hydrogen atoms together. We break the bond. Okay? So what's the take-home message to learn from this analysis? Something maybe you haven't thought a lot about before is that in molecules there are empty orbitals. The empty orbitals represent a wave function that an electron could adopt if it had higher energy. It is the place an electron would go if you promoted an electron from the bonding orbital to the antibonding orbital. To do that, you would need to have a photon that has just exactly this energy difference between the antibonding orbital and the bonding orbital. And this is, in fact, how molecules absorb light or visible light or UV light. If the photon has the right energy, it can promote an electron from a lower energy orbital to a higher energy orbital. And then sometimes chemistry can happen. I find students struggle with the concept of an empty orbital being there. How can you have something that's nothing? And the answer is that the math exists whether or not there's electrons there. And so the antibonding orbital represents the place where an extra electron could go. Okay, questions about that? Yeah?
Does that mean when electrons are promoted from the bottom to the top, it would split the compound?
If an electron is promoted from the bottom to the top, would it split the compound? It depends on the compound and how many bonds it has. In the case of hydrogen, where you've just got one bond, then yeah. Okay, what else? Yeah.
For that question, in the case of hydrogen, would it go to the antibonding orbital, or would it just split back into A?
So that's a good question. Would it just split back into A and B on its own, or would it go all the way up there? I don't know technically, and we won't worry about a distinction between those two. Yeah. Others? Okay, for those of you playing along at home, this is the origin of the not octet rule, but for the first row, the 2-electron rule, right? And this is why we don't make helium molecule. Helium has the same atomic orbitals as hydrogen does and would form the same molecular orbitals. Tell me how this diagram would be different for helium. There'd be an electron here, right? So just for a moment, if we're pretending this is for helium, we would start out like this. And that would mean if we formed a bond, we would also have to fill the antibonding orbital. There is zero advantage whatsoever to have two helium atoms form a bond, because you'd have to populate both the bonding and the antibonding orbital. That's the origin of the octet, of the 2-electron rule. And we'll see in the second row, we have not only the 2s orbital, but we have three p orbitals, 4 atomic orbitals, and so that's going to be the origin of the octet rule. All right. So we've now talked about sort of MO theory and hydrogen, but hydrogen is the simplest and perhaps boringest of organic molecules. In fact, it's an honorary organic molecule because it doesn't even have carbon in it. While I'm at it, I'm going to say that when we talk about organic chemistry, that means the chemistry of molecules that have carbon in them in general. We use the term organic not in the way it is used in food products and other kinds of products, meaning like sustainable agriculture and not using pesticides and other delightful things. In fact, I get irritated, though it's stupid irritation, but when I go to the grocery store and I see, ooh, an organic apple, like, buddy, all the apples are organic. They all have carbon in them. I realize that's not what they mean with that marketing term. But anyway, trying to figure out whether, yeah, why not? So there's, years ago, scientists thought that there was a fundamental difference in molecules that were isolated from living things versus non-living things. And this is where the term organic and inorganic came from. It was almost though they supposed that there was a special life force in molecules that came from living sources, and that therefore you could not make a molecule from a living being from stuff that was not living. And the person to show that that was incorrect was a chemist named Friedrich Wöhler, who made the molecule urea. And urea was an organic molecule that was well known. You could isolate it from urine, which is delightful, and you can go read the history of science to figure out how they did that. But Wohler made it from some inorganic precursors, and I forget what it was, ammonia and isocyanate or something like that. He wrote to his friend, "I cannot hold my water, so to speak," which I think was a urine pun. I've learned to make urea without kidneys at all, whether of dog or man. He made this molecule with inorganic starting materials, and that killed the idea that a molecule had to be derived from a living thing in order for it to be organic. So now we use the term organic to just refer to molecules that have carbon in them. This is not an editorial about the term organic as used in the food industry, so take it for what it's worth. But I want you to understand when you see labels like that they're not saying that the apples that are not organic don't have carbon in them, because you have to have carbon to be an apple. All right, so end of soapbox. Why don't we take a few minutes, go stretch, go drink, whatever, and we'll start back at the top of the hour.